We're going to be talking about the summer packet that you guys will be working on for Honors Algebra 2. Make sure that you guys go ahead and skip around the video if you guys need to. Find specific examples of certain problems that you want help on or whatever you need. Just go ahead and go wherever you need to go in this video, but just know that it is here for your benefit. I'm just walking through all the examples in the summer packet. I'm not actually doing any of the problems that you guys are working on, but I just want to make sure that I can explain to you guys how to go through those types of problems. All right, let's get started. So, first off, we have properties of exponents. So, as we can see here, we have a to the power of m times a to the power of n. So, this property says that if I'm just multiplying two exponents and they have the same base, as we can see these are both a, then I can just add these exponents. So, a to the m power times a to the n power is the same as a to the m plus n power. That's all it is. So, for instance, here we have x to the third times x to the fourth. Well, as we can see, they have the same base. They both have the base x. So, therefore, I can just add these exponents, 3 and 4. So, our answer would actually be x to the 7th power here. Because, again, I'm just adding these two because we're multiplying. Our next property of exponents, we have a to the m power divided by a to the n power. So, last time we saw multiplication, and when we were doing multiplying, we added. This time we see division, and if we see division, we're going to subtract our exponents. Again, this only works if our base, if the number that is being raised to the exponent is the same. And in this case, they're both a, so it is the same. I can subtract these exponents. So let's go ahead and see this. See an example of this. X to the 7th divided by x to the 4th. Again, they have the same base. The base is x. So I just subtract my exponents. 7 minus 4 will give me 3. So our answer would be x to the 3rd power. All right, next. I have a power raised to another power. So we have a to the power of m. That entire thing is raised to the power of n. So if I see my exponents right next to each other, they're just hanging out right next to each other, that's when we multiply those exponents. So a to the m raised to the nth power is the same as a to the m times nth power. So we just multiply these two whenever they're right next to each other with multiplication. So this is a power to a power. So for instance, we have x to the 4th raised to the power of 3. Well, I just multiply these. 4 times 3 gives me 12. All right, next up. A times b raised to the power of n. So as we can see, we have two numbers here, a and b, and they're being multiplied by each other, and that's raised to the power of n. What that is saying is I can break this apart into two different numbers. So for instance, if this was 100, I can break down 100 into 25 and 4. So I could say 25 and 4, I can say 50 and 2, 10 and 10, anything like that. Just know that you can break it apart into two different numbers, and both of those numbers will still be raised to an exponent. And in fact, it'll be the same exponent that's on the outside. Now, of course, these two are still being multiplied, so I can go ahead and continue working on it if I need to, after the facts. For instance, if this was 100, it would be, let's say 50 and 2, and then I can just do 50 and 2 raised to whatever power it is and find a simplified answer as well. But that doesn't always work. For instance, we have 3x squared raised to the 3rd power. Now, if we recall, this would be the same as 3 to the 3rd power times x to the, I see that they're right next to each other, so we're going to multiply those, x to the 6th power. Well, 3 to the 3rd power, that's the same as 3 times 3, which is 9, times 3, which is 27, x to the 6th power. And there it is. So again, we're still using that same concept that we just used, multiplying those exponents out to get that 6. And then, of course, I'm just breaking it apart. So both of them get the 3. So both of those get 3. All right. Let's continue on then. Next up. Again, I have this whole chunk, a divided by b, this ratio. And I'm raising that whole ratio to the power of n. Well, what that means is that n can go to both of these once again. So this is the same as a to the n power divided by b to the n power. So therefore, again, this exponent just goes to both. That's all that's happening. So if I have y over x, that's my ratio, raised to the third power, well, I just give this third power to both of these variables, which leads me to y to the third power over x to the third power. And that's it. All right. So a quick little property that we need to make sure that we remember. Anything raised to the power of 0 is 1. That's always going to be the case. So if anything's raised to the power of 0, it's always equal to 1. In this case, a cannot equal to 0. So I can't have 0 raised to the 0 power. That's not allowed. But I can have it be any other number besides 0. And anytime that that is a different number and it's raised to the 0 power, you'll always get your answer as 1. So 5 to the 0 power, 1. 2x to the third power, y to the second power. Again, I'm just going to spread this 0 to everything. This gives me 2 to the 0 power times x. Well, again, this is a power raised to a power, so this would be multiplying, if we recall our properties. So 3 times 0 is 0. And then 2 times 0 is 0 as well. Well, if everything is raised to the 0 power, that's just equal to 1. All right. Now, negative exponents. You guys are going to see negative exponents quite a lot this coming year. Negative exponents are extremely useful to get used to, and they're not too difficult. Anytime that you see a negative exponent, if I want to get rid of this negative exponent, I take the whole thing. Take this whole thing, sorry. Whoops. And I just put it all over 1. If I put whatever's in the denominator, because again, if we recall, a to the negative n power is the same as a to the negative n power over 1. That's the same exact thing. If I switch this, if I flip these, then this n will become positive. So anytime that I flip it over the ratio, then this n will become positive, or my exponent will switch from positive to negative. So this will turn into, this will turn into 1 over a to the n power. So again, if I put this into a fraction, if I move this to a denominator, the exponent switches from positive to negative or from negative to positive. So again, it's just all about putting this into a ratio. So again, as soon as I put it into a ratio, and this goes into the denominator, because it's currently in the numerator, as we can see right here, as soon as it goes from numerator to denominator, it goes from a negative to a positive. Now similarly, if I had 1 over a to the negative n power, and I were to flip these, this would become a to the n power. So again, as soon as I flip the numerator and denominator, this will either turn from negative to positive, or as we saw over here, negative to positive as well, just depending on which way you're going. So just keep that in mind. So for example, x to the negative 3. I see that this is a negative exponent. I want it to be positive because we don't want to deal with negative exponents. Negative exponents are more difficult to deal with, and they're harder to see when you're trying to graph things by hand. So just try and switch these to positive. So in this case, if I want to switch this to a positive, all I need to do is put this entire chunk underneath 1. So it turns to 1 over x. And now that this is in the denominator, now that switched from numerator to denominator, this turns positive now. So this is now x to the third power instead of negative third power. So that's the main difference. As soon as it goes from numerator to denominator, it flips from negative to positive. Now, if I were to switch this to from denominator to numerator, this would turn from positive to negative. So it just depends on which way we're going. All right. Next up, a to the negative n times divided by b to the negative n is the same as, well, again, I just talked about if I flip whichever side I'm on with the numerator or denominator, the exponent will change from negative to positive. So if I were to just flip b and a, then this negative attached to the b would turn positive. This negative attached to the a would turn positive as well. So if I want to turn this positive, then I just flip these over, and it turns to b to the n power over a to the n power. Now, this could also be written as b over a raised to the n power. Again, we learned this property a little bit ago, that if they're both raised to the same property, I can just put it on the outside, or if it's on the outside, I can give it to both as well. Just depending on which way you want to go. So just keep that in mind as well. All right. X to the negative third divided by y to the negative fourth. How can I get this into a simplified form? Well, if they're both negative, I want to turn them to positive, so I need to flip these around. So this would turn into y to the fourth over x to the third. Again, if it's negative, I want to turn it to positive, so it goes on the opposite side. All right. Next, we have a over b, this ratio, raised to the negative power of n. Well, again, I'm dealing with a negative, so if I want to switch that, I just flip my ratio. So if I flip it, it turns to b over a, so that's the main difference. This is a over b, this is b over a, and it goes from negative to positive. So let's try it out. X over y to the negative third power. So again, I just flip my ratio, y over x now, and it turns to a positive power. Now I can even go a step further and say this is the same as y to the third over x to the third. That's okay as well. Either of these answers is okay. Just know that you can play with these to get further along. So if you get stuck on a problem and you're right here, and you still got work to do on it, break it into two different parts and see if anything cancels out. Just get used to playing with these exponents, though. They will play a key role in this coming class for you guys. All right. Next up, properties of radicals. So we dealt with radicals throughout the year, so some of this should be somewhat familiar for you guys. But just keep in mind that these will continue on, and the more practice you get with them, the better off you'll be. So the first one that we have the square root to the power of n. So again, this is the nth root. Now I can plug in any number for n, and this won't change. So usually it's a 2 if nothing's there. Or if something else, if it is raised to, if it's the square root of a different power, say the third root, this would be a 3, fourth root 4, fifth root 5, all that type of stuff. So n can change numbers. Typically it'll be 2 though. So we have the nth root of a times b. Now if that's the case, properties of radicals say that I can take this number, whatever it is on the inside, say that this is 100. Whoops. Let's just pretend that this is 100 for a second. So this would be a is equal to, let's say a is equal to 25, b is equal to 4. I can say a is equal to 10, b is equal to 10. I can say a is equal to 20, b is equal to 5. So there's all sorts of numbers that I can take from 100. And then those numbers that I can take from 100, well, I can just put them into different square roots. So it doesn't matter what numbers you choose from. Now, of course, the easiest one for us to use here would probably be 25 and 4 because they're perfect roots. However, you don't necessarily need to use 25 and 4. I can use 10 and 10, 20 and 5. Those are all okay, but the most simplified one would be to look for perfect squares out of these. So if you can find perfect squares, then I can take the square root. So just keep that in mind. It doesn't always work out that way. Sometimes you'll be dealing with like a cube root or something, and you need to get comfortable with those. But just keep in mind that oftentimes square roots are the way that you want to go with these. So let's try this out. Square root of 50. Well, if I were to break this out, some numbers that multiply to be 50. Well, let's see. We got 25 and 2. What else do we have? Well, we have 10 and 5. We have 50 and 1. Right? We have 4 won't work. Well, we have 4 and 12.5, but we won't deal with decimals right now. Let's see. We got 5, 6, 7, 8, 9, 10, and we're back around. So we have all these different numbers. So I can break this down into a couple different things. This is the same as the square root of 25 times the square root of 2, which is the same as, well, if I were to take the square root of 25, and this is why I want perfect squares, because out of all these numbers, the only one that deals with a perfect square is 25. So I'm going to use that 25. What is the square root of 25? Well, It's 5, plus or minus 5. So I'm left with 5 times the square root of 2. Now again, if there's nothing in between, it just means that we're multiplying. So these are the exact same thing. So this turns into 5 radical 2, and we're finished with that. So again, that's where we can see it. Now, if you want to keep it underneath the square root sign, just start off with and be like, okay, this is the same as 25 times 2, and then break it apart into 2 different square roots from there, radical 25 and radical 2, and then take the square root at that point. You can do that. Either way is fine, whichever way you're more comfortable with. All right, next up, the opposite applies as well. If I have the nth root of a times the nth root of b, notice that these are the same. They both have an n, so they're both in the nth root. They could both be the square root or the cube root, but they need to be the same here. So both of these need to be the same, either not showing anything, both a 3, both a 4, whatever it may be. A and b do not need to be the same numbers. From here, I can combine these, so I can say, okay, this becomes the nth root, because again, they're both n already, of a, whatever number a is, times b. And those are both underneath the square root sign. So this is all this property is saying. If I have these two that have the same nth root, then I can just multiply the numbers underneath and put it all underneath 1. So let's go ahead and try that out. Square root of 2 times the square root of 3. Now, both of these are the square root because it's 2 here. There's nothing there. So I can go ahead and combine these underneath the same one. So this is the same as the square root of 2 times 3. And I know 2 times 3 is, of course, 6. So that's our answer. All right, next up. This is the same type of thing with the exponents. If I have the nth root of the ratio of a divided by b, then this nth root can go to both a and b. So that turns to the nth root of a over the nth root of b. So if the whole thing is being taken the square root of, I can break it down into a square root in the numerator over the square root in the denominator. So for instance, if I have the cube root of 5 over 8, this can turn into the cube root of 5 over the cube root of 8. Now, we want to simplify these all the way. I'm not going to simplify the cube root of 5 because that'll give me a very small number, probably an irrational for us. Cube root of 8, though, well, what number multiplied by itself 3 times will turn into 8? Let's start. 1 times 1 times 1 is 1. 2 times 2 times 2, well, 2 times 2 is 4, times 2 is 8. So therefore, the cube root of 8 is equal to 2. So this is the cube root of 5 over 2. All right, next, the square root of 200. So now we're using all those properties that we just learned, and we're going to try and simplify these as much as possible. So if I see the square root of 200, I'm going to go ahead and break this into 2 different square roots. So I need some numbers that will multiply to be 200. Well, here's a perfect square, 100 times 2. Well, what's the square root of 100? Because this now turns to 100, the square root of 100 times the square root of 2. Well, the square root of 100 is just 10. And the square root of 2 is radical 2. So this is the same as plus or minus 10 radical 2. You don't necessarily need that plus or minus there right now, but just know in the future, whenever we take that square root, it's going to be plus or minus in front. So you can have that there if you'd like after you take the square root. Right now, I don't mind if we just talk about it as the properties, because again, I want to make sure that we have the properties down. But plus or minus 10 radical 2, that's perfectly fine. But if you have 10 radical 2 right now, that's perfectly okay as well. All right. Next, we're taking the square root, the mth root of the nth root. So these are 2 different numbers. M and n are not the same. If this is occurring, if I have m times n and they're not the same number, then what I'm going to do is I'm going to multiply those 2 numbers. Now, again, if there's nothing there, if you see just an empty square root sign, what number is hidden right here? Well, the number that's hidden right there is a 2 if there's nothing there. So just keep that in mind. If it's blank, it's the same as the square root of 2. So we're just going to take these 2 different numbers, and again, if there's nothing there, it's a 2, and we're going to multiply those. And then from there, we'll have the m times nth root of whatever we're dealing with on the inside of our radical. So if we take a look at this one, we have the cubed root of the square root of 64. So if we think about this, what number should go right here if it's blank? Well, that should be a 2, because it's the square root if there's nothing there. So this will give me 3 times 2, which is 6. So I now have the 6th root of 64. So what number that's the same that when I multiply it by itself 6 times will equal 64? Let's go ahead and check. 1 times 1, 6 times. Well, you guessed it, that's equal to 1. Let's see what 2 does. Well, 2 times 2 is 4, times 2 is 8, times 2 is 16, 32, 64. So therefore, the 6th root of 64 is equal to plus or minus 2. And in this case, it's plus or minus 2, because if I did this all negative, negative 2, and we want to check here, because this will not always be the case. This will be positive 4, negative 8, positive 16, negative 32, positive 64. So in this case, it's plus or minus 2. And just so that you guys know, if this number is even, it's always going to be plus or minus 2. If that number is odd, it's just going to be plus. So very important that we know that for right now. That will change slightly once you guys start dealing with imaginary numbers more so. But know that right now, if this is even, it's going to be plus or minus, because, again, it'll turn out positive at the end. However, if it's an odd number, if this was a 5 or a 9 or something like that, if it's an odd number, then it's just going to be positive. Because, again, the only way that we'll reach a positive number on the inside here is if it is positive. Say, for instance, it was a negative 64 for this. Then when I'm trying to do this, well, I wouldn't get negative 64 when I multiply negative 2. So this would be gone. So again, it needs to stay, if this is positive on the inside here, this needs to be even to be plus or minus. If it's positive on the inside here, and this is odd, then it can only be plus. It cannot be plus or minus. This would need to be gone. So keep that in mind. And again, it comes down to this fact of we're just doing multiplication. All this is saying is what number multiplies by itself 6 times to equal 64. If it was 5 times, then, well, let me show you. If it was 5 times, 3, 4, 5. Well, negative 2 times negative 2 is 4. This is 4. And this is still negative 2. 16 times negative 2 is equal to negative 32. So as you can see, there's no way that I can get a positive number at the end here for this to be plus or minus. So that is why if it's odd, it's going to be negative underneath. If it's even, this is an even number, it must be positive. And that's one of those things that you'll pick up more so as you work on these more and more. But just keep that in mind as you're going through. It comes back to this idea that we're just multiplying these numbers. If I multiply an odd number of negatives by itself each time, I'm always going to come out with a negative at the end. If it's even, it'll always come out positive at the end. It's just a pattern that you guys will realize over time. All right. Now, if a square root is positive, this is when this works. If a square root is negative, then we start dealing with imaginary numbers, which you guys will learn more about over time. And the more that you guys play with those, the more comfortable you'll get with those. So, the square root is positive. And I have the the square root of n, root n of a, raised to the power of n. If I were to do this, well, the nice thing is that the n and the n cancel each other. And when this n cancels over here, that means that the whole square root sign is now gone. So that leaves me with just a. So if these two numbers are the same, if these two numbers n and n are the same, then they cross each other out and I'm just left with a. So the nth root of a raised to the nth power is equal to just the number on the inside, a. So for instance, the square root of 5 squared. Well, again, what number belongs in here if there's nothing there? A 2. The 2 and the 2 cancel each other because they're the same number. And my answer is just 5. That's all I had to do for these. All right, next up. Numbers are the same. Cube root and cubed, they cancel each other out, which leaves me with whatever number's on the inside here. In this case, it is -8. I got to have that negative there. Very important that we don't forget that. All right. Same thing. This time, if the exponent is no longer on the outside but on the inside, these ends will still cancel each other, and it'll leave me with just the number on the inside, a. So same type of thing is happening here. We're just seeing that the ends are canceling each other out and leaving us with just the variable or the coefficient on the inside of our square root sign. So, once again, we have the square root of 5 squared. What number belongs right here? Well, a 2. So the 2's cancel each other out, which will just give me 5. Another way to think about this is it's the square root still. If I were to do 5 squared, that will give me 25. The square root of 25 is equal to plus or minus 5. So in fact, this could be plus or minus here if you'd like, because again, we're taking the square root. But I'm not going to hold you guys to that strict of a standard quite yet. Just get in the habit of realizing, hey, this could be plus or minus, this could be just negative, this could be positive. Keep an eye out for those types of things. Play with these numbers, see if they make sense. If they make logical sense when you're multiplying them all out, then obviously you're doing it right. If they're not making sense when you multiply it all out, then start looking through this, start asking questions, make sure that you're understanding why it's not coming out the way that you're thinking it should. All right, and again, this can be plus or minus. All right, next up, multiplying a polynomial. So this should be review from Algebra 1 for you guys. You guys are going to be working on this type of thing for quite a while in Algebra 2. Very important that you know how to do it regardless. Once you get into calculus and start doing the chain rule, you're going to be needing to know how to do this anyway. So important just progressively for you guys to get better at this and just to know what you're doing with these easily. So, distributive property. We've done this a lot throughout the year for you guys. Just make sure that you know how to do this. It's not going away. It'll never go away. So just keep that in mind. The distributive property says, if I have a number on the outside of parentheses, so this parentheses is just a chunk. That's the way that I'm going to think of it. This is just a chunk of an equation. And I have a number on the outside of it. Now, as we can see, there's no operation in between the parentheses and this 5x here. So if there's no operation here, that means that we're multiplying. So I'm going to multiply this 5x by the entire chunk, by the entire parentheses here. So this would give me 5x times 2x and 5x times -3. And I just draw this to show that, hey, I'm multiplying through the parentheses. I'm multiplying it by both numbers here. Not just one, but both. So 5x times 2x, well, 5 times 2 gives me 10. X times x, again, this is x to the first power times x to the first power. Well, we learned earlier that if that's the case, I just add these because they're the same base, x and x. So that give me x squared. 5x times -3, well, 5 times -3 is -15. X to the first times x to the 0, because again, anything raised to the 0 power is just 1, so this is the same as it not being here. Well, again, they have the same base. I add these together. 1 plus 0 gives me 1. So this leaves me with 10x squared minus 15x. And again, I'm just multiplying through the parentheses. That's all distributive property is. All right, multiplying polynomials. So in this case, we're multiplying two binomials. It's called a binomial because bi means two, nomials means terms, and terms are separated by plus or minus signs. As we can see over here, we have these two bubbles here. That's what I'll call these for now. These are bubbles, the parentheses. That's what I refer to as bubbles. And within this bubble, I have two different terms because it's separated by a plus or minus sign. So here's one term, 4x. Here's my second term, 5. So this is a binomial because it has two terms. And then I have a second binomial, 3x minus 2, because again, two terms. So I'm multiplying these two things with two terms. Now, that leads us to FOIL. You guys have hopefully heard of FOIL in the past. This is just an easy way to remember that we're multiplying. Now, if you're like, okay, it's just double distribution, that's fine. Double distribution means I'm taking my first term, I'm multiplying it through the second parentheses. I take my second term, I do the same thing. I multiply it through the second parentheses. That's what FOIL tells us. So FOIL is just the order that we work in. FOIL says I follow this order: first, outside, inside, and last. This is the order of my multiplication. So I have these two bubbles here. I multiply first my first terms in each bubble. So my first term is 4x and 3x. So 4x times 3x is first. Well, that will give us, 4x times 3x will give us 12x squared. Next, I do outside. Well, my outside terms for both bubbles, well, 4x is on the outside and negative 2 is on the outside. They're the most outside terms of the two bubbles. They're on the outside of the parentheses, as we can see. They're at the very edge. So I multiply those two next. 4x times negative 2 gives me negative 8x. Next, I go to the inside terms. Well, if 4x and negative 2 are on the outside, then our inside terms must be 5 and 3x. And as we can see, I already multiplied 4x by both terms now. So when I multiply 5 and 3x, I suddenly get 15x. And then our final one is last. So my last terms, well, let's think about this. They're the last terms in both bubbles. So this is my last term in the first bubble. This is the last term in my second bubble. So I multiply positive 5 by negative 2, which will give me negative 10. So that's the order of operations for multiplying binomials. First, outside, inside, last. FOIL. From here, I combine like terms. So we're close to being done. So like terms must have the same variable and exponent. So I see x squared. There are no other x squareds here. I see x. I'll have negative 8x and positive 15x. Those are like terms. I can combine these two. Negative 8x plus 15x leaves me with 7x. The negative 10 does not have a like term, so I just bring it on down, leaving me with my final answer as 12x squared plus 7x minus 10. And that's how we multiply our first binomial. Next, the product formula. So these will be extremely useful. They're just shortcuts, so keep that in mind. The product formula says that if I have these two numbers being the same in both, so for instance, this is, if I were to just use an example, this is 2x plus 3 times 2x minus 3. So again, they're the same terms, so 2x and 2x, 3 and 3. The only thing that's different are these signs in the middle. I have a positive and a negative. So if you were to see something like this, then all I have to do to solve this, now you can FOIL still, so if you're like, I'm not comfortable memorizing this yet, I'm okay with FOIL, you can do that. But this is a shortcut. If I do x squared, so whatever my number is, my first term in both parentheses, if I just square it, minus my second term squared, I'll have my answer. Or if they just flipped, so again, all that happened is this is now negative first, this is now positive first. If you notice, if these flip, nothing changes. Same exact thing. So again, if these are just opposite signs, positive and negative, but everything else is the same, square your first term, minus square your second term. That's it. So let's try it out. X plus 5 times x minus 5. So again, we notice that x's are the same, so I just square it. I know that my y's are the same, and again, they're opposite signs, so I just do minus, and then I square it. That's it. Try our second one. x minus 5 times x plus 5. Again, I square my first terms, x squared. And then from there, again, they're opposite signs. So I'll square my second term and make sure that's minus. So same exact answer on both of these. The only thing that's different is the order that they're written, so nothing really changes. So keep that in mind as you work on these. Just a little useful tip for you guys to know that nothing will change. The order does not matter when we're multiplying. That has not changed at all for us. Algebra basics are still in play. All right, and then again, here are the answers. So I'll go ahead and leave this up for a minute. If you didn't want to use that formula I just showed you guys, you can still FOIL. So again, first, outside, inside, last, and first, outside, inside, last. As you can see, this is what happens, because usually we have 4 numbers when we FOIL. We get negative 5x and positive 5x. So those are opposites of each other. They cancel each other out, which leaves us with this x squared minus 25. That's why these are so different compared to this one that we worked on earlier, because this came out with 3 terms. These are only coming out with 2 terms, and the reason why is because they cancel each other out right here. So again, that is going to stay the same, and if you are more comfortable FOILing, you're not quite comfortable memorizing that quite yet, feel free to keep FOILing. It will take you more time, however, and it is good just to get to know these shortcuts for you in the long run. All right, product formulas. So product formulas say that if I have the same thing raised to the second power, so this could be x plus y squared or x minus y squared. It will change very slightly depending on whether this is plus or minus. And this is kind of leading towards Pascal's triangle, Fibonacci sequences, stuff like that. So this is where math starts getting very integrated with nature, and patterns are starting to arise, and special circumstances are occurring, which makes this very useful information to know in the future. So the product formula says if I have x plus y squared, then this turns into x squared plus 2xy plus y squared. So I take my first term and I square it. Then I add 2xy. So I multiply 2 times these 2 terms multiplied by each other. The reason that we do that is because when we FOIL, let me show you real quick, x plus y times x plus y turns to x squared plus xy plus xy plus y squared. So the reason that this 2 comes about is because I have 2 xy's, right? So if I were to combine these like terms here, this would turn into x squared plus 2xy plus y squared. So that's where this 2 comes from. I'm combining these 2 terms. Combining these 2 terms here. So again, if you're like, I'm not sure where this is coming from, I don't know how to get here, separate it out into 2 different binomials, because again, squaring it just means that I have 2 of them, and then FOIL. You can still FOIL right here. So anytime that you have 2 binomials and you're just multiplying, you can always FOIL. Just know that this is a shortcut though, and these shortcuts are extremely useful to know. I'm going to go over Pascal's triangle briefly in just a bit. Pascal's triangle is something that you must know for shortcuts. Very, very useful, especially when you get to really, really, really large numbers for this exponent here. Once you get to really large numbers for this exponent, multiplying it all out using FOIL each and every single time, distributing, takes way too long. However, Pascal's triangle simplifies it so that we can do it very quickly without the need of a giant calculator or anything. It makes it very simple for us. So let's try this out. 2x plus 3 raised to the second power. Now try and do this one without using FOIL. So if I were to do this, I take my first term, take my first term, 2x, and I square it. So 2x squared will give me 4x squared. Again, I'm squaring both of these. Plus 2 times, well, x times y, so 2x times 3 gives me 6x. Plus y squared, well, my y is just 3, so plus 9. So our answer is 4x squared plus 12x plus 9. And that's it. That's all we have to do. As long as we remember that formula, x squared plus 2xy plus y squared, we'll get our answer very easily. Now, can you FOIL? Absolutely, you can FOIL. If you FOIL, you'll still get the same exact answer, 4x squared plus 12x plus 9. So just keep that in mind. It's just a little shortcut that you guys can use, very useful down the road. This is actually the next step in multiplying these polynomials. So learning these shortcuts, extremely useful. All right, now change to a minus. So all that happens when it changes to a minus is our term in the middle switches from a plus to a minus. So this is the only thing that changes here, this minus sign. That's it. Can you still FOIL? Yes. Will it take longer? Yes. But it's still an option. So let's try it out. 2x minus 3 squared. So same type of thing. I take my first term and I square it. So 2x squared will turn to 4x squared. Because again, it's 2x squared, which is the same as 2 squared times x squared, which is 4x squared. That's where that 4x squared came from. Next, it's minus, because again, this is a minus sign here, minus 2 times xy. Well, x times y is 2x times 3, which is again 6x. And then plus y squared, well, my y is 3, so plus 9. If I were to write it all out, I'd have 4x squared minus 12x plus 9. Would it work if I FOILed it? Absolutely, I'd get the same exact answer. The only difference is between our positive and our negative is that this second term is now negative. And when we see Pascal's triangle in a minute, you'll see that it's very distinct on whether it's plus or minus. So, Pascal's triangle. So we notice a pattern here. X plus y raised to the second power is equal to 1x squared plus 2xy plus 1y squared. X plus y to the third power is equal to 1x cubed plus 3x squared y. Let me go ahead and plug in a 1 here. Plus 3x to the first power y squared plus 1y cubed. X plus y to the fourth power is going to be longer. It's going to be x to the fourth plus 4x cubed y plus 6x squared y squared plus 4x y cubed plus y to the fourth. Gets long. This continues due to Pascal's triangle. So I went ahead and I drew Pascal's triangle right down here. Let me go ahead and open it up a little bit. And it's very easy to memorize. So to make Pascal's triangle, you start off with a point, 1. And then I have 2 1s right underneath it. That's how we're always going to start off with. It's going to make a triangle, so we know that's going to expand outward. Next, I'm going to have 1 on the outside always. Now, to find out what number is formed right here on the inside, I add these 2 numbers right above it. So 1 plus 1 is 2. Now, for our next row, 1 and 1. If I want to find out these numbers, I just add them. So 1 plus 2 is 3. 2 plus 1 is 3. Next, I start off with 1s. And again, if I want to find out these numbers, I just add them. So 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. Again, my next row, start off with 1s on the outside. What number do you think will be next? Well, 5 right here. 1 plus 4 is 5. 4 plus 6 is 10. 6 plus 4 is 10. 4 plus 1 is 5. And as we can see, it keeps going. So the way that I find out the numbers in the middle is I just add the 2 numbers right above it. And that's how all these numbers come to fruition. Now, this is called Pascal's triangle. Now, if I look back here, 1, 2, 1. Well, we can see that in Pascal's triangle right here. For x to the third power, 1, 3, 3, 1. I can find that in the third row. In the fourth row, 1, 4, 6, 4, 1. 1, 4, 6, 4, 1. So this continues based upon what degree we're at. So if I'm at 2, as we can see, we have 2 right after the 1, then it's 2. If I'm at 3, well, the 3 comes right after the 1, so I'm using 3. 4 and 4. 5, and would be a 5 instead. So based upon what degree we're at, based upon our exponent number, depends on which row I use, whether it be 2, 3, 4, 5, 6, so on and so forth. Pascal's triangle can go on indefinitely. Very easy to memorize. Just look for these patterns. Add them up. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4. 3 plus 3 is 6. 3 plus 1 is 4. 1 plus 4 is 5, and so on and so forth. So make sure that you guys work on memorizing this. Now, there is a small little thing that we need to watch out for during this. So, first off, the first thing that can get confusing with this is what we're starting with. So, as we can see, our first term is always x. So x is going to start off with an exponent of 3. Then once I hit the second term, x drops down to 2. So it loses 1. Move to my third term, x drops down to 1. So it loses 1. Move to my fourth term, x drops down to 0. So it disappears completely. Now, look at the y's. Y starts out at 0 because it's my second term. Then it slowly increases by 1, by 2, and by 3. So as my x starts off at the highest exponent it can go, which is, again, what we're starting with, what's on the outside, whatever our degree may be, starts out at 3, and then it loses 1 each time we go along the term. Y starts out at 0, and it goes up 1 each time we reach a term. Now, neither of these should go above our highest degree here. It should not go above a 3. For instance, in 4, right down here, when we're dealing with a 4 as a degree, our exponent should not go above 4. So that's how we can kind of keep track of this. And again, our first term starts out highest, and it goes down 1 each time. Our second term starts out at 0, and it goes up 1 each time. So that's how you guys can kind of keep track of that. Now, the last thing with Pascal's triangle. If I'm dealing with x minus y cubed, well then I'm always going to start my first term off as positive, and since it's negative here, since that's a minus sign, it's going to alternate. So it goes positive, negative, positive, negative. Let's say that this was a 4. Start out with positive, negative, positive, negative, positive. This was a 5. So we always start off positive, and it just alternates. That's all that's happening. So if this is a minus sign, and only if this is a minus sign, we'll alternate our signs as we go through. If this is a positive sign, everything's going to be positive. If this is a negative sign, we alternate. So this would be x to the 5th, y is 0, x to the 4th, y to the 1st, x cubed, y squared, x squared, y cubed, x, y to the 4th, and x to the 0, y to the 5th. So again, x's are decreasing, y's are increasing. So that's the way that Pascal's triangle works. Now, can I just distribute multiple times all the way through and then take each term and do that repeatedly? Yes, you can absolutely do that. Will it take you forever? No, but it'll take you much longer, and over time it could take you all night just to complete an assignment, rather than knowing Pascal's triangle and just soaring through these because you're like, okay, I know that it's third degree, x cubed, so I'm going to use this row, and then it's negative, so positive, negative, positive, negative. Or, oh, it's x to the 5th, so I'll use this row down here, and then it's positive on the inside, so I'll go positive, positive, positive all the way through. And then just keeping track of your x and y's. Now, if you want to write it out as this, and then take your whatever your x value is and plug it in, take whatever your y value is and plug it in, you can absolutely do that. That is perfectly fine. Just know that you're going to have to multiply by these coefficients out front due to the polynomials that we're dealing with. So hopefully Pascal's triangle makes a little bit more sense to you guys. You guys will have a lot of time over the next year to learn this more so, but I highly encourage you guys to learn it, because the sooner that you learn it, the easier that it is to multiply any polynomial, just because you already have it all set up based upon the triangle. Now, does this stop at 6? Absolutely not. I can keep going. 1, 7, 21, 35, 35, 21, 7, 1. And you may be like, Mr. Garner, it's always repeating on either side. Absolutely, that is the case here, and that will always be the case with Pascal's triangle. It should be symmetric on either side, which is extremely nice for us because we know where we're going. Next one would be 1, 8, 28, 56, 70, 56, 28, 8, and 1. So again, we can keep going. You can find any one that you need to, depending on where you're looking. There should be tables on the internet of Pascal's triangle if you're looking for like a really large term, say like 21, and you don't want to write it all out because you don't have enough room. You should be able to find charts on that to make it a little bit easier as well. But just keep that in mind. Learn Pascal's triangle. Learn how to create it. You don't need to memorize Pascal's triangle. You just need to memorize the little tips in there, like the exponents increasing and decreasing, as well as the plus or minus. As long as you know that you're just adding down to create the triangle, you don't need to memorize this triangle because you can always create it very easily. So keep that in mind, guys. I hope that this is more useful for you guys as you move forward. All right, so let's go ahead and try this out. Let's use Pascal's triangle. Let's raise to the third power. So I'm going to create my little Pascal's triangle. 1, 3, 3, 1. We're working with the third power, so it's this row. So therefore, we should have, this is the same as 1x cubed y 0. This is a plus, so everything's going to be positive. So plus 3x squared y to the first. My x drops down 1. My y increases 1. Plus 3x to the first y squared. Again, my x drops down 1. My y increases 1. And then lastly, plus 1x to the 0, y to the third. All right, now let's go ahead and plug in our numbers. So we now have 2x raised to the third power. Y to the 0 power is just 1, so I can just get rid of that. Plus 3 times 2x squared times y to the first power. Well, y is just 3, so times 3. Plus 3 times x to the first power. Well, that x to the first power is just 2x. Y squared. Well, y squared is 3 squared. Plus 1 times x to the 0 power. Well, that's just 1, so it cancels out. Y cubed. So that'd be 3 cubed. All right, let's use our exponent rules that we learned to go ahead and solve this. 2 cubed will give me 8x cubed. Again, this is the same as just cubing both of these. Plus 2x squared is the same as 4x squared times 3. So 4x squared times 3 will give me 12x squared. 12x squared times 3 will give me 36x squared. Right over here, 3 squared will give me 9. 9 times 6 will give me 54x. So plus 54x. And then lastly, 3 cubed. Well, 3 times 3 is 9, times 3 is 27. And I just want to go through this one more time right here. I did 3 squared, which is 9. 3 times 2 is 6x. So I have 6x times 9, which gives me 54x. Right over here, 2 squared gives me 4. 4 times 3 is 12. 12 times 3 is 36. And then, of course, this x is also being squared, so 36x squared. I just want to make sure that I hit on any missing points that may have been in there. So this works perfectly fine. This is our answer. Further, if you're like, I don't want to memorize Pascal's triangle, which I highly encourage you guys to do, this is the way that we just did this. You can always just use FOIL. So as you can see, I separated this into 3 of the same. 2x plus 3 times 2x plus 3 times 2x plus 3. I FOILed the second part, so I drew up a little wall here, and I FOILed the second part, which gave me 4x squared plus 6x plus 6x plus 9, which is the same as 4x squared plus 12x plus 9. From there, I took my first term and I multiplied it by everything in the second parentheses. I did the same with my second term, multiplied it by everything in the second parentheses, which gave me this extremely long chain, and then I combined them all together, all the like terms, which gave me 8x cubed plus 36x squared plus 54x plus 27, the same exact answer that we got with Pascal's triangle. So again, either way works. Pascal's triangle will be a shortcut in the long road, especially once you get to really large degree numbers where this is no longer a 3 but rather a 7 or a 9 or something like that, where you'd spend all day just multiplying numbers. Pascal's triangle makes it much faster. So please keep that in mind. All right. Again, we talked about this a little bit with Pascal's triangle. If it's minus, instead, that's the only thing that changed. We just alternate, always starting with positive. So our first one will always be positive, and then we just alternate. So positive, negative, positive, negative. That's always going to happen if this is a minus sign. Alternate starting with positive. So positive, negative, positive, negative. All right. That's all that's going to change. So this time, 2x minus 3 cubed. Once again, I'm going to use Pascal's triangle. And I'm going to use it when we hit the 3. So 1, 2, 3, that's the row that we want to use. So we have 1, 3, 3, 1. My x starts at 3, my y starts at 0. X will shrink, y will grow. So now I have 1, 3, 3, 1, x cubed, x squared, x, and x to the 0, y to the 0, y, y2, and y cubed. So from here I just plug in my numbers. First off, 2x to the third power will give me 8x cubed minus 3, because again it's a negative sign here, so I'm alternating. So we see that we have positive, negative, positive, and then this will become a negative at the end anyway because it's minus. So it is alternating here. So important for us to know that. Positive, negative, positive, negative. In fact, I'm just going to make sure that that is shown. These should be negatives here. All right. So from here, so we have x squared times y here, right? So 2x squared, which would give me 4x squared, times y. Well, y is just negative 3. So I now have, and if you're like, Mr. Garner, I'm starting to get confused with the signs, just remember at the end it'll always be positive, negative, positive, negative. All right, always alternating at the end. That's our end goal. It's just to make sure that these are alternating. During the actual process, I don't mind if they get a little bit mixed up, but at the end, always alternating, starting with positive. So this will give me 12x squared times 3. Well, 12 times 3 is 36, so I have 36x squared. From here, negative 3 squared gives me 9. 9 times 3 is 27. 27 times 2x will give me 54x. And lastly, 3 cubed is 27. Again, we're alternating. So negative 3 cubed is negative 27, which gives me this negative 27 here. Same exact answer as our previous one, except now it's alternating as positive, minus, compared to our first one. So just keep in mind that's the only difference if it's a subtraction sign rather than a positive sign and addition sign, is that our signs will just alternate positive and negative. All right, factoring polynomials, the GCF. So this is much easier. Factoring polynomials using the GCF. I look for the greatest common factor. Greatest common factor is the largest number that can be multiplied into both terms. We also need to keep track of variables. Very important that variables are kept track of here. So for this first one, 15x cubed is one of my terms. 25x is my second term. The biggest number that goes into both of these, that is the same number, is 5. Do they both have a variable that is common? Well, yes. This one has x cubed, this one has x. So I can also take out an x. So my GCF is 5x. At that point, I'm just going to divide both of these terms by the GCF. So 15x cubed divided by 5x, we just learned our properties of exponents. So x cubed divided by x will leave me with x squared. So 15 divided by 5 is 3. X cubed divided by x will give me x squared. Next, we have negative 25 divided by 5, which is negative 5. X divided by x cancels each other out, so we're left with our final answer being 5x times 3x squared minus 5. So largest number n variable, and it's the opposite of distribution. So what we were just doing, this is the opposite. I'm going from completely multiplied out, and I'm going back just showing what can be multiplied. So it's just doing the opposite of what we were just trying out. All right, factoring polynomials, factors of the same sign. So again, we've covered this throughout the year somewhat. I'm not going to spend too much time on it, but I do want to make sure that it is covered in this video. If this is the case, they have the same signs, meaning they're all positive. I start off with my a value. I take my a value and I multiply it by my c value. So 1 times 12 will give me 12. From here, I need numbers that add to be 7, our middle term. Multiply to be the number that we just found out. So 1 times 12 gave me 12, so I need numbers that multiply to be 12, add to be 7. So I take the number that we're multiplying to, 12, and I find out all the numbers that multiply to be 12, because there's a lot fewer of those than add to be 7. So numbers that multiply to be 12, we got 1 and 12, 2 and 6, 3 and 4, negative 1, negative 12, negative 2, negative 6, negative 3, negative 4. Out of all these, the one that adds to be positive 7 is 3 and 4. So I go ahead and I take those two numbers. I make my double bubble here, x plus 3 and x plus 4. And I put both those numbers, this 3 and this 4, inside the bubbles. Now what goes first inside these bubbles is whatever variable we're dealing with. In this case, we're dealing with the variable x, so x will go first in both of these. Both 3 and 4 were positive, so they stay positive inside the bubbles as well. And this is how we factor. And that's factoring polynomials with the same sign. All right, next up, factors of same sign. So this time it's a negative instead of a positive. Same process though. So I start off by taking my a value, multiplying it by my c value. Our first term always multiplied by our last term. Now, it's important to note that this is in standard form, meaning we're starting from our highest exponent and we're shrinking down to no exponents. So highest to lowest, least to greatest. From here, 1 times 12, once again, is 12. So I find out all the numbers that multiply to be 12. 1 and 12, 2 and 6, 3 and 4, negative 1, negative 12, negative 2, negative 6, negative 3, negative 4. Out of all these, which ones add to be negative 7? Well, negative 3 and negative 4. So I create my double bubble. I put negative 3 and negative 4 within it. And then what goes first is whatever variable we're dealing with. In this case, we're dealing with x still, so they would both get an x in there. So this leaves us with x minus 3 times x minus 4. And that's it. All right, let's try this one out. Go ahead and give it your best shot. Slightly different, once again, but same rules apply. Take a, I multiply it by c. So 1 times negative 15 is negative 15. Now I need the numbers that multiply to be negative 15, all of them. 1 and negative 15, negative 1 and positive 15, 3 and negative 5, negative 3 and positive 5. Now be careful. Which one of these numbers will add to be negative 2? Well, for negative 2, it would be negative 5 plus positive 3. So I create my double bubble. I get a positive 3 in there and a negative 5. Very important which one is positive and which one is negative, because 5 plus negative 3 is 2. Negative 5 plus 3 is negative 2. From there, I just put whatever variable we're dealing with. Again, it's x in this case, and both of those, and we're done. All right. Factoring polynomials where a is not equal to 1 and a is not equal to 0. So again, our a value is our first term here, 6 in this case. So, same rules apply. I take my a value, I multiply it by my c value. 6 times 10 will give me 60. So I now need numbers that add to be 19, multiply to be 60. So for 60, we got 1 and 60, 2 and 30, 4 and 15, 5 and 12, 6 and 10, and that's all of them. We also have the negatives, though. We can do -1, -60, -2, -30, so on and so forth, but I already see our answer. Numbers that add to be 19 out of all of these ones over here would be 4 and 15. So I make my double bubble. I have x to start off with in each, because that's the variable that we're dealing with, and then we have +4 and +15. Now, we're not quite done here. Usually we would be, but in this case, when we multiplied to start off with, we multiplied by 6. We didn't multiply by 1. So this is where it changes. If I multiply by a number other than 1, I now need to undo that process. So I multiplied to get started. Now I need to divide to undo this. So I divide both bubbles by 6. Now we must reduce all the way here. So this will give me x plus 2/3 times x plus 5/2. Now the key here for any of these types of problems is I cannot have a fraction here. So I need to take whatever number is in my fraction, if there is one, and I need to move it in front of my x variable in each bubble. So this leaves us with our final answer being 3x plus 2 times 2x plus 5. And that's it. We are now finished with this type of problem. And that will always be the case if our number is not 1. You're always going to have to divide there. You cannot leave this as is. Anytime that you're dealing with something other than 1, you must divide at the end, or else you won't get the same exact answer. Now, if I want to check my work, I can always just FOIL and multiply these out. And if I get the same answer that we started with, you're good to go. That is one way to check these, though, if you are curious about that. All right, next up. Factoring formula is difference of squares. So this time we have x squared minus y squared. As we can see, if it's squared, I just take the square root of both of these. That'll give me x and y, and then I just notice that one's positive, one's negative. That's the only thing that's going to change in this. So as you go through these, just know that it's going to switch to positive and negative if there's a minus sign in between, and just take the square root of both these terms. That's it. So in this case, 9x squared minus 16. I'm going to say a squared is equal to 9x squared. And then down below it, I can say b squared is equal to negative 16. So if I want to solve these, I'm actually going to just say that this is positive 16 for now. I'm going to treat this as a separate number, and the minus sign is just part of our equation. So to solve these, I just take the square root of both sides. I want to get a by itself. Oops. So a is equal to 3x. For my b, I take the square root. Square root of 16 is 4, so b is equal to 4. So I now have x squared minus y squared is equal to x plus y times x minus y. Well, this will give us, if I plug in 3x for a and 4 for b, this will give us 3x plus 4 times 3x minus 4. That's our final answer. Again, you can FOIL these out to check your work. Important that we know this, that if it's subtraction in the middle, one's going to be positive, one's going to be negative inside our bubbles. That'll always be the case because we got to cancel out that middle term. So that's how you do difference of squares. Difference of cubes. This is where we start learning about SOAP, and you guys will be covering this in Algebra 2. Just know that SOAP is going to be extremely useful for you guys. SOAP is an acronym that stands for same, opposite, always positive. This deals with the signs that we're dealing with within these. So as we can see, this is with Pascal's triangle, 1, 2, 1. And this is just dealing with difference of cubes. So as we can see, it's raised to the third power. Difference means subtraction, so we have subtraction in there. And how we deal with this is it's always going to be Pascal's triangle for the second one because it's dealing with cubes. So this is Pascal's triangle. This is the 1, 1, 1, 1, 2, 1. That's what we're dealing with there. And then we have x minus y in front. So if I see that we have subtraction here, it's always going to start off with same sign. So my start off with the same sign, there's x minus y. Then I go to opposite sign. So same, opposite. Well, the opposite sign of minus is plus, so that's why this turns to a plus there. And then always positive, meaning our last sign will always be positive no matter what. So that's where SOAP comes in. Same, opposite, always positive. It deals with the signs that we're dealing with. As for the rest of it, we have Pascal's triangle in the second portion. In the first portion, we just do x minus y. Whatever x is, and whatever y is, we just do x minus y there. So, again, knowing SOAP will be very useful for you guys. Just stands for same, opposite, always positive, and it's always dealing with what we start off with. So if it's difference of cubes, we start off with whatever problem they give us. If we see minus, we just do SOAP. If we see positive here, we just do SOAP once again. So if it was positive, x cubed, and you'll see this in the future slide as well, it turned to same, opposite, always positive. So again, same, opposite, always positive. So as you can see, the only thing that changes for the sum of cubes is whether it's just positive or minus in the order that we go in. So as long as you remember SOAP, you'll be good to go. All right, almost done. A fractional expression is a quotient of two algebraic expressions. As in any fraction, the denominator may not equal 0. Division by 0 is not permitted. So what they're saying is that we're going to be dealing with fractions, and we cannot have 0 in our denominator because that will give us an answer as undefined. And in fact, on your calculator, it will give you an error. So we cannot deal with dividing by 0. That's not allowed for us. We can divide by numbers very close to 0, but not actually 0. A special case of fractional expressions is the quotient of two polynomials. So if I have a polynomial, x squared plus 3x plus, 2. If I have that, and I'm dividing by x plus 1 times x minus 3, that's what we're dealing with here. So this is a special case of fractional expressions is the quotient of two polynomials. So this is the quotient of two polynomials here. This is referred to as a rational expression. So again, quotient of two polynomials is the same as a rational expression. Follow these 3 steps in simplifying fractional expressions and rational expressions. So step 1, factor the numerator and denominator if possible. In this first one that I just wrote up a random example, if I can factor it, I factor it. Step 2, determine any values that would make the denominator equal to 0. Well, in this case, what would make the denominator equal to 0 down here? Well, what if I said that x is -1? Just as a hunch, I plug in -1 for x. That'll give me -1 plus 1 times -1 minus 3. Sorry, that should be a minus 3. Well, -1 plus 1 cancels out and gives me 0 times -4, which will give me 0. So therefore, I can say x cannot equal -1. Can you find another number that x cannot equal that will make this turn into 0? Well, what if x was 3? If x was 3, this other bubble would turn to 0, right? And I'd still be multiplying by 0. So x cannot equal -1 or positive 3. So that's what we mean. What numbers will make the denominator equal to 0? Once we find those, we know that we cannot have it be set equal to those numbers. So x cannot be -1 or 3. Step 3, remove any factors of 1, factors that are the same in the numerator and denominator. So this is my favorite part. We cancel if anything can cancel. So if it's the same in the top and the bottom, we cancel them out and they're gone. So that's how we deal with these rational expressions. So, my best advice, break it into pieces, simplify top, then bottom, after determine what cancels. So for our first one, x squared plus 3x minus 10 over x squared minus 25. The first thing that I'm going to do is I'm going to go ahead and factor this top portion. Let me go ahead and go back. So I take my a value, multiply it by my c value. This will give me negative 10. I'm looking for numbers that will add to be 3 and multiply to be negative 10. So 1 and negative 10, 2 and negative 5, negative 1 and 10, negative 2, positive 5. Out of all these, the ones that will add to be 3, negative 2 and 5. So I have x minus 2 times x plus 5. Then on bottom, we have a difference of squares. So in this case, my a value is x, my b value is 5. And since it's difference of squares, the signs need to be switched. So it'd be x plus 5 times x minus 5. So again, opposite signs, and then difference of squares, so it's going to be the same bubble, just opposite signs. All right, now that we know that, do we see anything that x cannot be equal to? Well, yeah, x cannot equal negative 5 or positive 5. So x cannot equal negative 5 or positive 5. From there, do we see anything that cancels? That's the same on both top and bottom. Well, yes. X plus 5 is on top, x plus 5 is on bottom. They cancel each other out, my favorite part of all this math. And I'm left with my final answer being x minus 2 over x minus 5, where x cannot equal 5. Now you may be like, Mr. Gardner, can it still not equal negative 5? Well, it can now, because we were able to cancel that out. It just means that when you graph this, you may see something strange at negative 5. You may see something strange at positive 5. That's when you start dealing with asymptotes in your graphs, holes in your graphs, stuff like that. You're going to start seeing some strange things that are happening, but that's when graphs get really interesting. So keep in mind rational expressions. Play with these on your calculators. Try them out, see what happens. See what happens when you enter in this whole thing, or even when you just enter this in. See what the graphs look like. See what it means when we hit 5 on these, or what it could look like. And guys, we'll be drawing these up in the future. Get some practice in with these. This is probably the more fun math. It's a little bit more challenging. A lot of content all in one. Just a lot of learning that you've done over the past, all combined into one section. However, this is when stuff starts getting really interesting in mathematics, because it gets a little bit more complicated. All right. Go ahead and try this one out. I'll be going through it in just a sec. I believe this is our final one. Yep. So let's go ahead and try it out. All right. I take my a value, multiply it by my c value. 3 times negative 2 gives me negative 6. Need numbers that add to be negative 5, multiply to be negative 6. So I got 1 and negative 6, negative 1, 6, 2 and negative 3, negative 2, positive 3. Out of all these, the one that adds to be negative 5 is our first one, 1 and negative 6. So I now have x plus 1 times x minus 6 for the top. And then on the bottom, I'll get to that in just a sec. Now, I multiplied by 3 to get started. I must divide by 3, because it's not a 1 that I'm multiplying by, so I must divide by 3. If it's a fraction, I move it out front. If it divides nicely, I leave it as is. So I'm left with 3x plus 1 times x minus 2. Now on bottom, I do the same thing. A times c, that'll give me negative 10. I need numbers that add to be 3, multiply to be negative 10. So I have 1 and negative 10, 2 and negative 5, negative 1 positive 10, negative 2 positive 5. Out of all these, the one that will add to be positive 3 would be negative 2 and 5. So I now have x minus 2 times x plus 5. Now, looking at this, the difference is I do not need to divide by 1 here, because that won't change anything. So this is good to go. On top, I need to divide by 3 because my a value is not 1. So I now have x minus 2, I'm just going to move this over, times x plus 5. Can anything cancel on both the top and bottom? Yes. I have x minus 2 on both top and bottom. They cancel each other. My answer is left as 3x plus 1 over x plus 5. What value can x not be? Well, x cannot be equal to negative 5. If x is negative 5, our denominator turns to 0, and we cannot divide by 0, so x cannot equal negative 5. All right, this is it for the summer packet review. If you guys have any questions, let me know. Let Mr. Hendrickson know. This will be available for you guys to use at any time. Just make sure that you guys complete that summer assignment for yourself. If you guys need anything, please let me know. Other than that, I hope that you guys have a great rest of your summer. Hope to see you next year, and good luck in Honors Algebra 2. I'll talk to you guys soon. Take care. Enjoy your summer.